Good afternoon, everyone. Welcome to class. We have we're moving on to a new topic today. Last week we looked at was it last week? No, we did a tutorial session last week. Today, before that, we spoke about renewable systems integration. There's one section of the syllabus that I'm going to give you some material to go over. All right. Once we look at that, then we basically have one more topic and the module will be done. All right, so we're going to deal with that today. And we're going to focus on the substation today. All right, so we're going to look at substation fundamentals. Just talk about some key aspects of substation operation. So today will be a lot of, hopefully, will be a lot of discussions. I sent you some figures in Schoology. I hope you have been able to access those. We'll see them in the presentation, but for reference, you have them with you. So you can go back and look at them and to gain a better understanding after we have gone through today's class. So let's get started. So let's just start briefly about what a substation really is, and then we look at some of the other fundamental issues regarding it. So by way of definition, it's a part of the power system that acts as that bridge between generation and end users. Okay. Of course, you have the transmission system. Yes, we spoke about that before. We know about that. But here we're dealing primarily with that link between the end users and the power system. And although I'm saying this, there are going to be some variations to it. But in essence, this is what the substation is used for. And I'm a little hesitant in giving this definition because you can classify a substation based on, on several things. You can look at it in terms of application, in terms of the service that it provides, or the voltages, or just by virtue of where it is located. So we can classify substations on that basis. However, generally speaking, it is that bridge between transferring electricity from generation or from your generation sources to your end users. And by end users here, we're not just speaking of basic consumers, all right? An end user can be an industry, right? A whole industrial complex. So I want us to always bear that in mind. So we're not just talking about your regular customers when we speak of end users. So as I said just now, we can classify substations based on the application. What is it being used for? Yes. We can classify it based on service. We can look at them or classify them based on the voltages that are present in the substation. Or we can look at it from the perspective of the location and design of your substation. Now, obviously there would be a limited list, but our purpose is not to go down and look at everything. So I'm going to just touch on a couple of these, look at some of the designations on the application, on the service. Of course, we mentioned those for the operating voltages and the locations or design. Yeah. And then I will touch on a few on the application and service. All right. So that's how we are going to proceed. So let's start with application. What are some of the substations as listed under application? All right. So under application, we have your step up or step down substation, your primary or secondary substation. We have distributions if it's being used for distribution purposes. Yes. We can also have mobile substations, industrial substations. So these are some of the substations that would fall under application. Right? So you have step up substation, step down. So the only purpose of these substations is to move the voltage from one level to another, and vice versa. So we bring it from one level to another, or up to another, and or from one to down to another. All right. So we are either bringing it higher or lower. Okay. And the voltage at which you'll be supplying your energy will have certain requirements. So in terms of the space in which you're operating, you may not be able to have a 138 kV line, for example. And I'm just throwing that out there. So you may not be able to have a 138, but you can have a 69. So to go in a particular direction, you have the 138 coming into the substation, you bring it down to the 69 and move it on. Similarly, you may have the need for reducing the losses given the distance over which the power would be supplied. And so you may require a 138 instead of your 69 installation. And so you'll need that step up. But let's discuss a couple of these. As I said, I will not go through all of them. I will just go through a few other relevant ones. So for your step up transfer substation, and what I'm showing you there on the right, I don't want you to think that it is what must obtain for a step up substation. Right? This isn't necessarily what a step up substation must look like. But this is a picture of a step up substation. So if you were to go, for example, down by Hunts Bay, heading east, if you look on the left rather, heading east, if you look on the left, across from the power station, you would see such a substation. All right. So if you look to the right, passing the power station, you'll see the step up substation. All right. Of course, you have step up transformers on the Hunts Bay facility. And I'm using Hunts Bay because it is one of the facilities that is quite visible, meaning generating facilities. Or better yet, for those going out to the airport out by Rockfort, all right, either coming down Mountain View Avenue, you'll see the substation just outside the power station, and so you have a step up there, but you also have some step down transformers, which provide power further out into Rockfort. Flour mills, you have a dedicated feed up to flour mills, and then feeders going out to Rockfort. So you do have a step down there, but you also have step up facilities that will bring it up to the transmission voltage. And I think Rockfort ties back into Cane River. All right. All right. So your step up substations are directly linked to generating facilities. We know that here in Jamaica, our generation is coming at us at approximately 13.8 kilovolts. I'm trying, I think, you know, I have to be cautious with how I say this, but in terms of my own awareness of existing facilities, the highest generation voltage that I'm aware of is 24 kilovolts. If they have gone above that with increased technology for cooling, I am not aware, but for what I'm aware of, it's at 24 kilovolts. So that's what we are generating at maximum worldwide. But of course, we have voltages in terms of transmission up to 765 kilovolts. So obviously, you're going to need step up substations to facilitate that. All right. And we are fully aware that the higher the voltage transmission, it means that you're lowering your losses because you have a lower current flowing. And so your power losses, your real power losses, your P losses would be less. All right. For your step down substations, they will receive the transmission voltage and provides input to the distribution substation. So what we're saying here is that it's not, I want to understand that this is not similar to the distribution substation. So these substations would possibly let, and because we are using such low transmission voltages here in Jamaica, it makes it a little difficult to help you to appreciate what we are talking about in terms of the need for a step-down substation. So in the UK, for example, the distribution substations are taking in 132 kilovolts, coming down from 400 kilovolts in terms of the major transmission lines. So at 132, you would take that down and supply it to a lower substation, which would be a distribution substation. And then the distribution substation would pass the voltage out on the streets, okay? Additionally, coming from these step-down substations, that 132, as the second point is highlighting here, may go directly to industrial facilities. All right. So in the case of a UTEC, I mean, we are coming from the old days, and Kingston is the only place, and I need to double check that. I know we have there's a voltage standardization in terms of distribution of 24 kilovolts. But at one point in time, we had some older transformers which were taking in voltages at lower values coming into the university. So we would have had some smaller substations here. So at present, we may be taking in 24 kilovolts. Because of our size, we have to provide our own substation. So what we are saying here is that for industrial facilities, they may take the straight 132 or and I'm talking about in a jurisdiction such as the UK, they may take the 132 kilovolts. All right. In Jamaica, a large facility such as, and I mentioned earlier that there's a dedicated feeder going into the flour mills. So they will take 24 kilovolts. All right. So from that step-down substation, you can then tap off those high voltages which are going into industrial facilities, and those facilities would then provide their own distribution of lower usable voltages, get it down to their 110, their 220, etc., their 415, that sort of thing. All right. But coming from the utility itself, yes, you'll be getting 24. All right. I hope we understand that. So the step-down substation is not about distribution. It is providing a lower voltage for the distribution substations. So I can't think of any that we have here in Jamaica, but it would mean we are taking it from the 138, and from the 138, we then supply the substation with, say, 69. And from that 69, it goes down to 24, which is then fed onto the streets. I hope that is clear. All right. Any questions? All right, moving right along.
Sir?
Yes.
Yes, I was just asking about I was trying to get the different, but I think you already answered the question, to differentiate between the step-down substation versus the in
distribution.
Jamaica, that is.
You mean versus the distribution?
Yes, sir, because taking it from 69 to 24K, that would be considered stepping down, a step-down substation, correct? Or is it
in the strict sense of what we're talking about here, it would not be, because what we're saying, we're providing input to the distribution. So it's taking it from the high transmission to a lower, or if you want to call it a subtransmission voltage. So because of the fact that our voltages are so low, which is what I said earlier, it is hard, it is really not I don't want to say the done thing, but in terms of the input to our distribution substations, their input are primarily 69 kV. So we take in 69 kV and bring it down to 24, and the 24 is what on the streets. But the 138 is what we transmit across country. You do have transmission along 69, but if we are moving from, say, out by Duane Park, Washington, rather, not Washington, Duane Park, over by 6 miles, yeah?
Yes, sir, that's 130.
That's taking some 138 all the way into Trelawney and Manchester. Right? So those are going across country. If you look, you see the lines going over the hills. So that's taking some 138. But in terms of, if you want to call it local transmission, then that's at the 69 level. So when we talk about the step down will be taking it from the 138 to the 69. But the 69 is not a distribution voltage. That's the point I'm making.
Okay, sir, understood.
Distribution voltage is 24.
Yes, sir.
So the step down is taking it from the 138 to the 69. Then the 69 is the input to the distribution substation, which
yes,
then
sir,
is 24. I hope that makes it a little clearer.
Yes, sir. Thank you very much.
All right. So on the distribution now, this is where we now take that 69. And I'm using 69 because of the fact that that is what we're using here on the island. All right. So that will now take the 69 and provide the 24 kilovolts, which goes onto the streets. All right. Now that 24 kilovolt on the streets, yes, is fed into the pole-mounted transformers. And those transformers are what you now get your 450 and your 220, your 110. All right? Which is what us as customers would use locally. What do you call that? So, as I had mentioned UTEC earlier, right? So I had mentioned UTEC earlier. UTEC would then receive a 24 kilovolt feed. And we will provide our own, we will be required to provide our own transformers, which then provide supply to the various facilities at whatever voltages we require. All right. Okay. Again, what I am showing you here, it's not that this is what a distribution substation must look like, but this is a picture of a distribution substation. Right? And I have said it before, but we just want to make sure that people are clear on that. Okay. Continuing on application, we also can have what are known as mobile substations. So you have a mobile substation, and this is where you use in temporary installations. Right? You can have a major construction going on, what you have access to, maybe the transmission system. But in order to complete that construction, even before you put in the substation to supply that area, you may need to have this mobile substation. Additionally, you may need to be rolling in this mobile substation if you have, I think here in Jamaica, what we do is just to roll in a transformer, really. So if you have, I recall there was a major fire out there in St. Anne recently. They just rolled in the transformer, switched from what was in the substation onto the mobile, so they could then deal with the damaged unit. And so the customers would not be out of power. Now, I know you haven't done it yet, and I say yet cautiously, but this is part of what we stress from a power system protection standpoint. That the objective of the supplier, right? The objective of the utility is to make the available to the customers electricity. That's the objective, right? And so whatever systems that need to be put in place to ensure reliability, ensure that power is always there, then that is what will be done. All right. Contrary to some of the lambast things that the current utility here in Jamaica gets, right? That's their real objective, to provide reliable electricity to its customers. And we'll discuss this briefly when we look at introduction to protection. All things being equal, we should start that next week. All right. Also, we have industrial substations. Okay. Now, again, this is not what it has to look like, but this is one. It would look no different from another substation, distribution substation. But the key here, when we talk about industrial substations, is that the utility, again, would provide a subtransmission level voltage to the facility. So while
saying that again,
they would supply a subtransmission voltage to the facility. So in Jamaica, whilst our industries are, within the scheme of things, relatively small. So they would be supplying the full 24, but maybe, in other parts of the world, they may be supplying a 132 kV to the facility. That facility would then put in their own substation, which is what we are looking at here. They put in their own substation to distribute power within the facility. All right. Body clear now? Okay.
Yes, sir. I have a question.
Sure.
Suppose it is that the industry that we are working with that is located in a residential area. Can the industrial substation be used to increase the voltage that goes in, or is that's not a scenario that exists?
All right. That's a very good question. Um, the reality is that industries are not supposed to be alongside residential areas. That's the reality. Now, one of and I say that because the considerations that the utility company will have to make for industrial slash commercial facilities is completely different from the considerations for residential, right? Now, one of the things that you would have noted, well, no, let me not say that to you because it wasn't asked specifically. But that lab 2 that you did, one of the important lessons that you should have taken from it is that increased reactive power will obviously mean that there would be an increase or increased demand for reactive power would mean that there would be an increase in the apparent power. Everybody cool with that? Now, the reactive power would be, or the reactive power demand would be coming from use of motors and that sort of thing. Agreed? Ms. Michael?
Yes, sir.
All right. Now, if I'm putting in a lot of motorized loads in my home, or should I say my facility, then the utility company will have to make the necessary provisions to supply that, which means that the transformers, which are rated in volt amperes, would have to be of the right capacity to supply. No. When people, like we do in Jamaica, and a classic example is in the Eastwood Park, for those who are familiar with that area of Kingston. Right? Now, Eastwood Park was well, I say it was, but supposed to be a residential area. Still is a residential area. All right? Now, Eastwood Park is under siege from businesses. Now, the utility company, in trying to upgrade its facilities, may come to customers trying to find out what sort of load they are using, and they want to know what you have in your house. But our natural inclination as a society is to assume that the utility company's only goal is to see what's inside your house in order to increase your electricity bill. Is that a fair statement?
Yes, sir.
Exactly. Now, what they are actually doing, they have to know what the demand in a particular area is in order to efficiently size their equipment. So if people are in the residential areas carrying out commercial activities, it's going to put a strain on the utility company. So this is a very long response to your very short and your very short question, right? Which is that ideally industrial facilities are usually appropriately zoned and ought not to be mixed with residential, or even commercial, because the considerations in terms of what the utility needs to do in supplying them are completely different.
Okay, sir. I understand better now.
All right, good. All right. Thanks for that question, Ms. Michael. All right. Now, from a service standpoint, we have converter stations, we have switching stations, and of course, we have collector stations. And I'm going to speed up a little now. You can refer to the recording for any further clarification. But please keep the questions coming, even though I'm going to speed up. For your converter stations, we don't have these in Jamaica. Yes. However, these facilities are used, quite in a number of places in areas such as Europe. Let me explain quickly. A converter substation has equipment that can change frequencies, right? Now, for it to change frequencies, what it would need to do is to convert it from AC to DC, and then from DC to AC. All right. We know that the fight between Maxwell and Edison was about AC and DC. All right. Did I send you guys that?
So in Tesla, sir.
Tesla. What did I say?
Maxwell.
Tesla. Did I send you all that video? No?
Sir, it's not on the site, no, sir.
It was there. All right. Anyway, I'll put it.
Yes,
but
sir.
between Tesla and Edison was about AC versus DC transmission or distribution, really. All right. So, in order to move from before I talk about moving from, but in places in several countries in Europe, one of the biggest industry is that of electrical energy. So they sell electrical power. That's one of the big industrial commodity that is sold, right? France sells a lot of electricity because a lot of their electricity is produced using nuclear. And they will sell electricity to countries such as England, right? Now, France uses 60 hertz. England uses 50, which is why Jamaica is in this predicament, because we followed them, right? Most other countries use 60. And from your machines, you know that is, for use of a better word, a little more natural in terms of what we get from our generation. But that's not the debate right now. So these converter stations, what they are used for is to do just that. Move us from 50 to 60 hertz. Okay? Which is moving the AC to DC or DC to AC. All right? In order for the commercial exchange of electricity. You're switching substations. Yes? That's just it. We're switching. So you're moving supplies. Yeah. Switching our own lines. Biggest switching substation here on the island is Duane Park. Okay. One of our largest substations on the island, if not the largest. Okay. The other benefit of these substations is that it will provide some isolation under fault conditions. All right? But if you want to hear more about that, you have to come back in January. Okay? So our switching substations, without switching power lines, without necessarily altering the voltages. Right? They're almost seen as, if I use a better word, intermediary substations. Now, switching isn't the only thing that happens at Duane Park, so let us be clear on that one. Okay. Also, it provides isolation, and when we look at some bus bar arrangements later that may become a little clearer. And then lastly, in terms of service substations, we have what we refer to as collector substations, used in distribution power generation. Right? Now, as the power system evolved, or maybe I should say that first generation power systems were actively distributed. So you had little stations supplying, small communities. That's where we were. Call that first generation. And then second generation was that we shifted from those small generating facilities serving small communities to large power stations. Now that was really where Tesla came in. Yes, he's saying that let us do this using AC so we can put in large facilities and send it much further, right? And so that's where we moved. So we moved to having centralized generation, which was then distributed. And if I may say, third generation is that we then started to put in distributed generation. So we now brought back small generating facilities. So you have your little wind farms, you have your solar farms, you have your, hydro could be considered depending on the size of the hydro, right, as major facilities. But you get the point. We now have distributed generation, which is generation, small generation scattered across the network. All right. Distributed, or you may hear the term embedded generation. So they are now embedded into the system, which was looking from generation out. So it was generating facilities sending power out to consumers. So it was one-way traffic in terms of the electrical energy. With distributed energy or distributed generation, we now have power coming into the network from customers and from these other distributed facilities, distributed generation facilities. Now, for your collector station within your wind farms, and I may have sounded a little distracted earlier because I was looking for a photo I have of Wigton to show you just how the individual connections are made and then summed at the power station. But that's what the collector station is about. The power flow from multiple power sources is collected and then distributed to the grid by stepping it up to the transmission voltage. So if you go to Wigton, you would see them with a small substation on site. You would see the little collectors along the ground, all right? Come into that substation, and then the substation, at least Wigton 1, let me speak to Wigton 1, it then sends it up to the Spur Tree substation, which is now coming into at the transmission level at 69 kV. All right. So we have spoken about application. So substations based on application. We have substations based on service. And we also have substations based on operating voltage. So for operating voltage, this one is nice and quick. For your high voltage substations, we're talking about, yes?
Quick question, sir. Sorry to bring you back to the converter part though, sir, but my question is, as it relates to the frequency at which the voltage is produced, isn't it dictated by how many cycles per second of the generator itself, sir? And I'm speaking about the
the 60 cycles or the 50 cycles, depending upon the country, sir.
Yeah, but what I'm saying, remember for you too, I think we spoke about it not last week, the week before. We're talking about the conditions for you to have generation and being connected or interconnected with a system. Remember we spoke about that? Yes, no? Sir Blake?
I believe so.
You believe so? All right.
Yes,
You
sir.
haven't reviewed it as yet. Anyway, we did. One of the things we said is that you had to add synchronization. It had to be synchronized. So if I am selling power into the, all right, let's say we are coming from France, which is 60 hertz. If I'm going to sell power to England, which is 50 hertz, there has to be synchronization. It has to be synchronized, yes? Do you agree with that? Huh?
Yes, sir.
So what I'm saying, the converter station is where you would then convert it from 60 to 50.
Yes, sir. I get that part, but the part when you were saying that you have to convert it to, I think I misunderstand. I thought you said that you should convert it to DC, then to AC or something like that.
That's
so I was
exactly
saying,
what I said.
sir. So what I was thinking is, wouldn't by changing how many cycles per second, for example, it was at 60, by changing in the cycles per second to 50, wouldn't that be as simple as changing the frequency, or am I misunderstanding?
But the cycles per second is the frequency. What I'm saying, remember now, the power is produced at a certain frequency, which is based on the rotation of the generating unit and the number of poles, etc., etc. We agree on that?
Yes, sir.
All right. So that is what is being produced on the mainland, which is in France. So they are operating their system at 60 hertz. Agreed? Talk to me, no, man. Do you agree with that? Even if you're not sure.
Yes, sir. I agree, sir.
So they are at 60, but they are selling electricity to England, which operates their system at 50. Yes?
Yes, sir.
So remember now, in terms of the system itself, they are operating, the generators in England are operating at 50 hertz, just like it operates here in Jamaica. But in order for them to purchase power from overseas, so they're purchasing electricity just like they are purchasing rice. For them to purchase electricity and use it in their system, which is operating at 50, we need to convert the 60 to 50.
Yes, correct.
All right. So let us forget about the power system. Think of a solar PV system. Yes. When you get what the output that you get from your panels, I'm going to be troublesome now. The output you get from your panels, what is the frequency?
Sir, I don't know, sir.
Come on.
Zero, sir.
Zero. Why?
Because you don't have anything rotating or...
It's DC. Yes? There's nothing, no rotating part. It's DC. So you're getting DC from your panels. But we said it last 2 classes ago, right? That what you're going to then do to get it to AC is to do what? Come on, man, don't talk to me, man. We only have
Convert it, sir.
You need an inverter. All right? So you're going to need your inverter, and your inverter is going to produce that AC at 50 or 60 hertz. Because all of the equipment in your house, no AC them run by.
Okay, sir. So I think I understand, sir. Because what I was saying that maybe they turn down the speed of the generator to match with the 50 hertz.
Oh, no. They convert it to DC and then from DC to AC.
Yes, sir. I get it now, sir.
All right. So just like from your solar PV, which was DC, coming from the panels on the roof. Yes? When it comes into your inverter, that is then converted or inverted, if you use a better word. Inverted, and you get the DC, the AC being produced at 50 or 60 hertz. All right?
Yes, sir. Thank you, sir.
Not a problem. That's what I'm here for. So quickly, coming back to the voltages. We call a high voltage substation between 11 and 66 kilovolts. So our substations are at least high voltage because all of them has a minimum 24 kilovolts inside, right? So that is why you'll see the sign, high voltage. They tell you up front. So it's a high voltage substation. We're talking about extra high voltage, then we're talking about the 132 up to 400. All right? We run 138 as our highest voltage here in Jamaica. We don't need nothing bigger than that. In places like the UK, they go up to 400 kilovolts. In parts of the US, they go up to 765K. So those would be ultra high voltage substations. And of course, you have DC, right? So you still have DC transmission. So we call it high voltage DC. So HVDC, right? High voltage DC transmission voltage.
Excuse me, sir.
Yes.
That would be used in like is it telecommunication that mostly use that kind?
No man, in some areas they transmit in DC. It has some benefits. They don't come directly to mind, no? But I will look at it and get back to you. But in some instances, there are some benefits that, as I said, just don't come to mind at present.
Okay, no problem, sir.
From your HVDC. All right. And then lastly, in terms of specification, we talk about location. All right. And I'm going to pause here because I need to just run out, get something signed, and come back. For location, I just speak quickly to the two that would be of interest to us. For your indoor, when we talk about an indoor substation, and I hope you understand that there can be some overlap based on what we have discussed so far. So your indoor substation, yes, can also be a distribution substation. You with me? So we classify them based on operation. So for your indoor, on the roof, our closed compartment used for voltages up to 32 kV. An example of this would be your Hope substation. There's an indoor component to it. The distribution side of the substation is housed in a room on property. And for your outdoor, open air, and it's for voltages 66 and above. So I will simply tempt you by saying that if you're interested in going to visit these things, then I'll have to see you in January. All right. I'm going to pause here for a few. I'll be right back. right, let's go again. So that is what I will refer to as our introduction. So let's give you a broad introduction on substations. Some of the things that we need to consider. Now I want to zero in on the main focus for today, which are distribution substations. All right. I look at distribution substations, and anybody interested, we may, you're all know at year 4, or if you have an inclination towards power, we can do some work in terms of higher level studies and distribution engineering. Anyway, distribution substation.
Excuse me, sir.
Yes.
Remember the recording, please.
Thank you, sir.
You're welcome, sir.
What did I do? Oh, I stopped it. Imagine that. Thank you, Mr. Venner. Now, the purpose of your distribution substation is to lower the voltage from your transmission. And we said this earlier. And subtransmission. The subtransmission would be the input you would have gotten from your step-down substation, right? So from your transmission or subtransmission levels to a voltage that can be safely installed on the streets or on adjacent to the customer's premises. So in other words, your distribution substation will take the voltage from the 69 transmission level down to 24, which is distribution. All right. As I may have said in the past, the distribution voltages in Jamaica, there was a plethora of them, from 24, 2.3, 6.8. It was all over the place. All right. But no, there was a project some years ago which was known as the Voltage Standardization Program, which upgraded all the distribution to 24. Okay. So the purpose of that substation is just to bring it down to the voltage that can be safely used or moved around a particular area. So we now need to delve in some of the key things as it relates to distribution substation. Part of the limitation here is that the right of ways that may be available near to a customer's premises would make that low voltage necessary. And it goes back to what? To the question that Ms. Michael asked earlier, which is a very important question. Very important question that we need to appreciate, as far as power systems is concerned. Because of where an industrial facility ought to be, then you would not be concerned about the types of rights of ways that you'll be dealing with when it comes to a residential area. All right. Now, the towers that would be required for a 69, all right, would take up the land space, just 1 foot of the tower. Just one tower, in terms of the footing, may take up the land space of 2 homes. Now, I doubt you would want to have something like that in your backyard. But those are the facilities that will be required if you were going to be supplying 69 kV. All right. But within a community, within a residential community, what is on the pole is 24 kilovolts, and we are good with that. All right. Of course, you can have your spurs, which are your 415s, your 3-phase 415s going, down a little lane. You're not going to carry the 24 down that little lane just for, those few houses. Okay. All right. Now, within that distribution substation, you have certain equipment. You're gonna have your transformers. Of course, you need to take your voltages down to the distribution level, voltage level. You can have your circuit breakers, right? You have relays, all part of your protection, your lightning and surge protectors. You have bus bars, yes, and your bus bars, we have been using it. I mean, we have been talking about nodes in networks. Technically speaking, that's your bus bar, and where we have a source, this is where you start making the links with all that you have been doing. So those voltage sources that you may have seen in a network, in a circuit that we did in networks, those generators, those sources are really generators, and those generators are connected to a bus bar, which is a node, and those nodes, between those nodes you have resistance and you have inductance. Yes, I throw some capacitance in there too. Yeah, and those may represent the lines that goes between the generation and the node. All right. So I want you to now start making sense, because all of those calculations and that question you did in the mid-session, the per unit question, right? It was just a way of pulling you from networks into electrical power systems and show you that the two really are linked. Okay, so this is where you start now crossing the T's. You have dotted a few I's. We now need to cross the T's and ensure that our learning is for use of a better word, all joined up going forward. So you have your bus bars, you have your disconnect switches. Then you have voltage transformers and current transformers. These are used as part of your protection system. Now, not all these equipment will be used in our substations. All right. So you may not find voltage transformers in our substations, for example. I mean, you will definitely find current transformers, but the types of relays that you will find in substations may not be the same. Some relays, you may not need all of them. Yeah. So these things vary. Okay? The type of lightning protection that you'll have in one substation may not necessarily be the lightning protection you'll find in the other. But these are some standard equipment that you'll find in your substation. Now, some of the factors that will dictate the design and layout of your substation, some of those factors are shown. So you have your voltage. Yes. The voltage level would speak to things like clearances. Yes. Yeah. And we'll speak about that in a little more detail in a few minutes. So the design or the layout will be dependent on your voltage, the load requirements in terms of the density and the expected growth. Yes. Also the importance of the load. Now, I tell people that when I used to live in Papine, I was a happy man because I rarely had a power cut. But the power cut wasn't really about me. It was because I live near to the university hospital. All right? Because that's an important load. All right? If you want to never have power cut, then you live near Judges. You have to work this thing out for yourself. But anyway, the other factors, availability of site space. If you are going into places where you don't have enough space, then the layout that you use will have to fit in what is available. The location of the site. And I'll speak a little more to this because only recently there was a court ruling here in Jamaica that spoke not specifically to substations, but to the whole distribution network of an area. Also, the protection system sophistication. And we'll talk about protection systems later on, and some general principles around protection. And so the protection system sophistication and cost. Because, as I said before, one of the primary objectives of your power system is to supply your customers and to provide them with a reliable supply. And that reliability will be closely linked to the type of protection that is employed. And protection can be from a one wire with your ground to a multi-billion-dollar system, right? And also, the design of your power system will have to give consideration to other substations with which it will be connected. All right? So, there's an interconnection, for example, between Upper Camp, Hope, and they are the primary substations going into the university hospital. But they, in terms of operation, it is such that if one fails, the other one will continue to supply the hospital. So the hospital will never be out of electricity. But of course, there are other things that are going into place in terms of seeking to provide their own electricity. But they would have to understand that they still have some dependence on the current utility provider. But the design per se will have to take into consideration the other substations with which it will be interconnected. So let's just delve a little into these, and then we will. That will be it for today. All right. Now, just a couple of notes here. In terms of functionality, all right, this may be the case even within the same company. So you'll have, based on just the functionality of the stations, you will have variations in terms of the design within the same company. So I'll design something for Hope completely differently from how I design it for somewhere in Bath, St. Thomas, or Negril, Westmoreland, right? The considerations may be completely different. Now, standardization would make life beautiful. So if for example, to my own chagrin and disappointment, I know half of you that I'm teaching here today, that in the next 10 years, I'll see you all in North America or the UK. I know that. Well, then again, COVID might change all of that. But that's it. You may end up working for a company that has several industrial facilities and different substations, and you may find that it will be best that these substations are standardized, because of course it reduces the time that you're going to take to come up with a new design for a new substation should you be opening a new facility. All right. So these are things that I wanted to appreciate, and I may be going into your research methods now. Yeah, I may be going into an area that I have no business going into. But get this clear, students. There is nothing wrong with referencing or looking at what has been done by other individuals, right? In your labs, we call it theory. Okay. In research or for your project, we call it literature review. Good. And when you go out into the working world, you call it reference. So you look at what people have done. There's no need to go and reinvent the wheel. If you go there and you see this is the design that they use for the substation, what you do is to take it, look look at it to the extent that it can be used for a new project. You don't necessarily have to start it from scratch, and that is something that you as engineering students need to appreciate. Yep, it's not always about new. It is about looking at what people have done, acknowledging their effort, and then put your own spin on it. Okay, but don't take it and spin it and make it and present it as your own. That's where you get into serious trouble. Anyway, back to standardization. It simplifies construction and maintenance. Right? So your maintenance program can then be simplified. You don't have to have a maintenance program aligned to a specific substation or facility. Whatever that program is, you can roll it out for all facilities if you have standardization. And of course, construction and maintenance. And then, of course, stocking of spare parts, that makes life easy. I know of one major facility here in Jamaica, major facility. They are in serious trouble because they're one of their generating facilities. They are struggling to find spare parts, and so they are scrapping one unit to fix up the other. Right? But all right, that's for another time. Okay. We also want to state, however, that overstandardization can result in the selection of substations that do not economically meet the needs of an area to be served. So that is why I said earlier that you look at what has been done. You consider it carefully, but you always then make the adjustments based on what is required for the project that you are looking at. So you make the necessary adjustments. So if the standard thing is that you have two double breaker, double bus, right? It don't mean that when you build a substation to serve that new community that is being built in the hills of Clarendon, that you're going to use double breaker, double bus. You may be able to do a single breaker, single bus down there, and the people will be happy. They don't mind losing power, once a year, right? You don't need to. So you have to consider these things. And remember, as I said, as engineers, your purpose is to save your company money. I'm not saying cutting back on quality of service. That's not what I'm saying. But save money whilst meeting the objectives of the company. All right. Now, one primary consideration is based on the distribution voltage. Remember, we said that voltage, and I had it at the top there. Voltage is one of the key factors in deciding on the layout of your substation. Right? And the highest distribution voltage that can be safely and economically installed in the available right of ways. So this one, it says safely. Now, I understand that this is a major consideration. I was just talking about you saving your people money. But if it is not done, then I have a problem. Okay? I don't think I need to emphasize that too much. In terms of voltage, you also have the conductor spacings. Now, the conductor spacings would be dictated by the right of way that you have, right? And the right of way the right of way dictate the spacing. The spacing dictate the voltage levels that you can work with, right? It also speaks to your ground clearance. In other words, the height from ground. Yeah? Now, the size of the load that needs to be served also determines the capacity of the substation. Right? What is the loading? So you're going to buy your transformer based on that. Right? what kind of load are you doing? Remember I said earlier, and you see, I come back to that beautiful question from Ms. Michael. Because the type of load, whether it's commercial, industrial, or residential, yes, will dictate the sort of substation that I build. So if I have an existing substation for a residential community, but the people in that community, everybody are open shop, everybody are open garage, everybody are open salon, everybody. Well, I suppose Portmore is a classic case, right? If that continues to happen, it means that the substation would then become inadequate. So zoning is important, you know. We hear now a lot of cries about what is happening on the hillsides. Yes, and it pains my heart to see what is happening. But at the same time, if we as a people don't get into the business of respecting rules in terms of buildings and that sort of thing, and ensure that things are passed and that they're in the right zones, if we don't become strict in those things, you know, we're going to continue having these challenges, and that those issues also impact your substation and the facility required to supply power to these customers. All right. Again, the importance of your load, critical loads, just like the hospital, are served with more complex substations. So one of the things we're going to talk about in a few minutes, yeah, we know we're running out of time, but we talk about the bus bar arrangements. All right. Now, some bus bar arrangements provide increased flexibility, but that flexibility comes at a significant cost. All right. So those are things that we would have to give consideration to. All right. So when we do the design in terms of the protection system that is applied, we are saying that it must provide maximum reliability and the speed of power restoration. So even if the hospital loses power, we must be in a place, or we must be able to return that power in as short a time as possible. What are some of the other considerations as it relates to load and voltage and space, right? We have to bear in mind that we're going to have growth in load, but growth in what type of load? So I suppose when we talk about load growth, persons are going to say, well, you know, yes, they must have had capacity there for increased load. So if a man put up, start run even a tire shop where he's running his compressor, the compressor put on reactive loads on the system because he's now running motors. Right? Now I know that may jar at our own need to do that which provides an income, or provides the wherewithal for our survival. But the fact of the matter is, it has some implications for the operation of the grid. All right? So we have to think about that. But load growth, so we might have excess capacity. Whilst we may not opt to put in the excess capacity up front because, for whatever reason, that may not be the acceptable decision. We may go for having a substation that will be easily expanded, so we can add capacity. Now, the other point is that if we have enough space, then we can play, we can have fun. Right? So if we have a lot of space, we have more design options. We can go to town. Right? However, in dense populated areas, these options can be severely curtailed. And we need to understand and appreciate that. Now, not only are we talking about curtailment in terms of the availability of land, but the land itself can be so expensive that you just have to use what you can afford in putting in that substation. Yes. And then you'll be forced to use a design that requires much less space. The other thing I wanted to mention was, for example, the visual sensitivity of residents. There are some places, and it happens, I suppose, here in Jamaica, that persons were not too happy to get up and see a windmill every day outside them bedroom window. Right? Now, when you're driving along the road down in St. Elizabeth there, and you look up on the hills of Manchester, and you see the windmills, they look quite nice, But I tell you, I kid you not, when you drive by those windmills, they are huge and they can become, well, I mean, I don't know if I can say this about an inanimate object, but they can feel a little intimidating in terms of size. I mean, you're driving beside them and you feel like an ant relative to these things. People don't want that. Same thing with the substation. People don't necessarily want that in their backyard. They don't want to see it. And so it creates or forces you to be involved in more expensive designs, right? Now I mentioned earlier the issue that played itself out in the courts recently, where persons in whole pastures, they won their court battle against the JPSCO in terms of underground versus overhead distribution lines. And also, even the substations that are in that area are such that if you have to deliberately go and look for those substations for you to see them. So they are partially, I know I'm stretching it a bit when I say this, but they are partially indoor substation, right? And so you are forced to spend more money. So it is the decision of the utility to recoup those money in terms of when you're going to develop that facility. If that is what going to be the selling point, a key selling point for the individuals who would be living in these areas, then they have to pay that developmental cost up front. Okay, if you're going to put the substation underground just to appease their sensibilities or sensitivities rather, then they have to pay for it. I hope you get the point there. All right. Okay. And now on the downside, we talk quickly about talk about substation grounding, and then we look at bus bar arrangements, and then I say goodbye to you for today. Any questions or comments? Or should I say, are you all awake?
Yes, sir.
Yes, sir.
Oh, yes, sir.
Yes, sir.
All right.
About
There, man, there.
Yeah, I hear a few sounds, so it sounds like enough people are awake.
Sir, but I've heard of that thing that you mentioned in regards to the whole pastures. They want the system to be underground. This was a United States. I don't remember what state it was to be exact, but the person wanted to live in a particular location. However, there was just high, I think it's a large transmission lines that were there in the area. There wasn't a lot of houses there, and he had to pay for his own generating unit and the utility company in that state would connect it to the transmission grid, I think, transmission lines to get his source of energy from that particular utility company. So he had to stand the cost of paying for that transformer in wanting to live in that particular location.
And I thank you for that. And that is something that happens here in Jamaica, where people just want to live off the beaten path, but they end up being very far from the supply, and they have to just pay the utility company some good money to get the supply to their location. Unfortunately, whilst that may be the case for the utility, when it comes to roads, all we need to do is to just walk through a path long enough, and then soon we'll see a road appear. But that's for another time. We only have half an hour to wrap this up.
Yes, sir.
But thanks for that.
Yes, sir.
All right. Substation grounding. Once persons are walking around in a power station or touching, the people have to work there. Let's get that clear. People have to work in there. We don't know when a fault will occur. And when the fault occurs, you can have dangerous voltages occurring between your legs, or when you're touching a piece of equipment. And one of the key ways of reducing this possibility is to have the earthing impedance as low as possible. Ideally, it should be zero, because we know that earth resistance, is supposed to be zero. That's not usually the case. So ideally, the earthing resistance within your substation should be about 1 ohm, right? 1 to 5 ohms, but let me just say 1 ohm, all right? And this is achieved in part by putting in what we refer to as a grounding grid or earthing grid. And all equipment, everything within that substation is connected to the grid. Now, I think I have sent you these photos, so you can have a look at it. All right. So here's a typical substation, and here's your grid. So all of this is your grid, and your grid would be right around the substation. So underneath, so before they put in the substation, they would basically dig out or excavate all of that area, put in the grid, yes, and then all the connecting points would then come up for your various equipment. So I want you to note that here we have that talk about the switch gear. So that would be your breaker. Note you have a mat. So when you're working on any piece of equipment within the substation, there will be a little mat, metal mat that you need to stand on. And that's for your own protection. Even though you have on safety boots, etc., you would have that. And that is the switch gear. And you see the little green thing there? That's showing you that it is connected to earth. Your transformer, connected to earth. All substations, and some of the things we kind of just pass them, but my purpose here is to increase your sensitivity to a number of things, so you won't just pass them anymore. If you look, all substations are fully fenced, and it's not just to keep you from thieving the equipment, but the fence posts are all connected to the earthing mat. Because although the company has the sign up front that high voltage keep out, right? You're still going to have people maybe hanging on to that fence, holding on to that fence. If you are holding on to that fence during a fault, yes, you shouldn't really have an issue, because all the fence posts will be connected to the earthing grid. All right. Now, a couple of ways that you can reduce the resistance to the grid. All right. Ready? One, in terms of depth. So the deeper you bury it, you can help to reduce the overall resistance. The number of meshes, so each of these, that's a mesh within your grid. Right? So the number of meshes within it. So you can increase the number of copper of meshes. Right? So if you make more meshes, then yeah? So that's 2. Thirdly, you have some rods here. You see these rods? Right? Well, they only show 2 here, but obviously there'll be more. If you can increase the number of rods. Right? So you have the number of rods. So that those are your vertical rods here. You can increase the number of meshes. So you'd use more wire. All right. You can make this, the grid itself, you can make it deeper. Now, what you'd also note, what they have here is crushed rocks. Right? What those crushed rocks do, they don't necessarily reduce the resistance of the grid. What they do is to increase your step and touch potential. Go again. So the crushed rocks, and if you note, you will not see a whole heap of bush growing in your substation. All right? And it's not only because of the rocks. Remember, they would have taken out the topsoil and put in the grid. So a lot of those shrubbery would have been killed in that stage. But outside of that, you also have the crushed rocks, which increases the step and the touch potential. In other words, it makes the minimum voltage at which you would be in danger. It would make that voltage a little higher. All right? But again, if you want to hear a little more of that, we talk in January. All right? So you can refer to this, your control room. That is where all your relays are located. That again is connected to your grid. Is there anything else I need to mention here? No, I'll leave that. The next, your bus bar arrangements. So your bus bar arrangements, one, they used to facilitate the number of circuits connected. So the number of circuits, meaning, you can remember we're still talking about a distribution substation here. So the circuits will be the feeders that goes into different communities. So down at Hope, you have 3 feeders. You have one going down, what that road name? Anyway, heading towards you. You have one going Hope Pastures Way. You have one going up Papi. Okay? So you have those distribution feeders which go out on the road. And I'm saying the number of circuits will be dictated by your bus bar. So in the sense of your bus bars here, we're not going to be looking at generation, even though generation technically is connected to it, because whatever is the incoming to the bus bar, to the substation, would be, technically speaking, your source. So when you are representing this, when you are doing a study on your substation, what you would establish is a grid point. So that grid point would be seen as your infinite bus. So that would be your input to your substation. All right? But generally speaking, we're talking about the number of distribution circuits when we talk about the number of circuits connected. The bus bar arrangement also speaks to maintenance. And of course, the minimum number of circuits required to be isolated during fault. I'm not going to spend a lot of time on this because that is really for the protection. Yes? And the arrangement that you ultimately use, will be based on the service requirement. What is it that you're really serving? Who are you serving? Yes. And then, is it worth it? What's the cost of providing this service? Yes. So what you use will be based on the service requirement, who you're serving, and two, what it will cost to provide that service. All right. So that's decision making. And I hope, ladies and gentlemen, and I say these things and I know that sometimes I annoy the life out of you. But I'm saying it, everything that you're doing, everything that I am saying today is based on the approach you take for your lab. You do your research, you look at the results, you have a discussion, and then you make a decision. So that would be applied to your bus bar arrangement. Okay? Who you're serving? What's the cost? What are the implications? The who you're serving will dictate what's the sort of flexibility that I need. Can these people be without power? If they are without power, for how long? Because that will now dictate the sort of protection that I'm using. Okay? All right. So the first one I want to talk about is a single breaker, single bus. So one bus bar, and to each circuit, you have a single breaker. Right? Very basic arrangement. It works. It is cheap, and it is simple. Right? Use that low voltage, but it doesn't offer much flexibility. The bottom line is, if you have a fault, it trip. You may have a reclose on it, but if you don't, it trip. Somebody have to go check, clear, and reinstall, and return to service. So for a single breaker, or single bus, single breaker, all right, I'm showing here 4 circuits. So you have these diagrams. Did you get the email? I know I sent it maybe about half an hour before the class. Did you all get the email?
Yes, sir.
Yes? No? Some of you got it?
So I didn't receive it.
I'm yet to receive.
All right. I sent it in Schoology, so you can look at it when you have the time. All right. So all these diagrams are already there. So what you'd need to do is to make the notes. The diagrams as shown are there. So here are your circuits. These are your circuits. 1, 2, 3, 4. So I'm providing 4 circuits. Here's the bus. That's your bus bar, and these are your breakers. So what that is saying is that each circuit, yes, so circuit 1 is being supplied from this single bus. So that's a single bus. All right? That's a single bus. And it is being supplied by 1 breaker. So 1 breaker manages that 1 circuit from that 1 bus. All right? I said earlier about VTs, that's something that we would talk about again if you come back in January. All right, so that's your single bus, single breaker. Now you have a single breaker, double bus with what we call a bus tie. All right, so your single breaker, single bus, it's quite similar to your single breaker, single bus arrangement. But it is used where you have at least 2 supply points. Remember what I said before, that the design of your substation will be linked to the design of adjacent stations. So if I have a substation that can get supply from 2 other stations, then I could have my single breaker, single bus with bus tie. I mean, single breaker, double bus with bus tie. Are you with me? So if I lose one, I just put in the bus tie and I'm good. However, that's not really the purpose. The purpose here is that, do we have this?
Yes.
All right. So with a single breaker, double bus, what is he saying with the bus tie? If I have a fault, then those will open. All right. So if I have a fault over here, all right, then that will open, which means that circuits 1 and 2 will continue to be served. These guys would not be served because these would be open too. But the bus tie opens and allows power over here. You with me? Because bus A would still be supplied by the incoming on that bus. Similarly, it provides greater reliability because if the supply for B is lost, right? If that supply is lost, I still will have all 4 circuits being served once the bus tie is closed. We understand the increased flexibility? So whereas for this one, if I had a fault on the bus, all of these would open. And therefore, all 4 circuits would lose power. In this case, only 2 of the circuits would lose power if I had a fault on one of the bus. All right? So it is, this is not totally lost. It is not all lost. But you still suffer some losses. All right? Okay. So we have talked about single breaker, single bus, single breaker, double bus with bus tie. And then just a further expansion, we have a single breaker main bus with transfer bus. Don't worry, if you remember all of this afternoon, then it means that, you know, I can give you the A and you just leave it. You know, but so don't feel pressured that all of this information is coming at you. All right. So next we have a single breaker main bus with transfer bus. And if we go back to what I said earlier, in terms of considerations, right? The bus arrangement is used to facilitate 1, the number of circuits, 2, maintenance, and 3, we consider the fault implications. And then, you know, what we use will be based on the service requirements and, of course, cost. So far, in terms of cost, the single breaker with double bus with bus tie, it may cost a little more than the single breaker single bus because I have the tie bus breaker included. All right. All right, so the single breaker main bus with transfer bus, quite similar to what we looked at before, right? It's a single bus. The difference here, do we have this? Finish writing. All right, silence I suppose means consent, so we move on. So I have my main bus down here. Under normal conditions, these switches are closed. All right? So those will be closed. And it means that we'd have supply. Let's say if a circuit 1 from my main bus would have it there. For this one, all right? And then for this one, okay? Now, if, as it says, if we go back to the note, we said that if we need to carry out maintenance, then we can use a transfer bus. So let's go and trace that. For your transfer bus, if you look over here, here's my main bus. Now let us say I'm working on circuit breaker number 4. So this one will be taken out. But we still need to get power to circuit 4. All right? What we will do, we close the tiebreaker. Okay? So we'd close that. Now we have energized the transfer bus. Once we have energized the transfer bus, we then close that. So you now get power from the main bus, through the bus tie, through that, and up to 4. So if I take out bus breaker 4, that's how I get power to circuit 4. Again, don't stress yourself that you can't trace all that. Today I've given you the circuits. Yes, you can go back, look at the conditions that we have laid out here. Yep, and then look at the operation. Okay. Next, single breaker, double bus. So now we are getting into where some important people live in our community, in the community that we are doing the design for. All right. So now we have a double bus, single breaker. What this is saying to us is that we can have supplies through my single single breaker, of course, being supplied from one of 2 buses. Yes? So one of 2 buses. Now, the challenge with this is that ready?
Yes, sir.
So here's bus 1. Here's bus 2. My circuits, circuit 1, circuit 2, 3, and 4. All right. Now, if you look on the switches between the 2 buses, all right, and if you look at the switches between the 2 buses, that's right here. Let me use red. So between here. All right. If you look on either side, you have normally open, normally closed. Yes? What that is saying, in a nutshell, is that both of them can't be closed simultaneously. That's all it is saying. So you can only get supplied from one bus at a time. So circuit number 4, yes, cannot be supplied from bus 1 and bus 2 at the same time. Can we see that?
Yes, sir.
Right. So in the event I have to take this out for service, I would then go to the normally open side. So I would close that and I would close that. So let me take out all of the ink here. So that would be closed and that would be closed if I have to take this out, right? But then I would close these in terms of providing protection in the event I have a fault on that. Are you with me? So if I get a fault on 4 while I have done the bypass, because the bypass would have been this up here, all right? So that's how I would get power from 4. Under normal circumstances, let me use the blue, I would have done this to 4. But if I have to take out the breaker, yes, I would have gone where you have the normally open. So 4, as it is now, under normal conditions, would have been supplied by bus 2. But in the event I need to supply from bus 1, then I have no problem. So what this is saying is that the reliability has increased. All I have done here, I now have 2 bus bars to supply my loads from. All right. I know I only have 5 minutes, and I have 3 more to mention. So for your double break and double bus, high flexibility. Don't worry too much about this January argument. But high flexibility, yes, very expensive, because I'm going to be using 2 breakers for each load. Breakers not cheap. All right. So in terms of the diagram for this one, yes. Your circuit 1, circuit 2, circuit 3, circuit 4. Here is bus 2, here is bus 1. Okay? What we're saying is that circuit 1, 2, and all the circuits are supplied by 2 breakers. So you have a breaker on this side, you have a breaker on that side, which service, in this instance, circuit 4. This one supplies circuit 3. That was circuit 2. So in the event I have a fault on this bus bar, all right? And based on your lab, you know that the more severe fault occurs the closer you get to the bus bar, or not. No, let me rephrase that. Your more severe fault occurs on the bus bar. All right. As you go away from the bus bar, the severity of the fault decreases. So you have that fault on the bus bar, it means that all of these would trip. But although they trip, the customers 1, 2 to 4, or the customers on feeders 1, 2 to 4, would not even know that they have had a fault. Because although all these breakers have tripped, yes, all these breakers would remain in service. So that the customers wouldn't even know what was happening. But, as I said before, expensive, and you would have to determine whether or not these customers are important enough for that consideration. All right, ring bus, high flexibility relative to the number of breakers. If you take one out, if you take out a breaker, nobody would know. Yes. But we have some other protection issues. Again, don't worry too much about that. January argument. All right. But we can take out a breaker and the supply is maintained. All right. So the question is, I mean, with this great level of flexibility, are we using four breakers, which is similar to the single breaker, single bus? Why then not use this? That is it. That's part of the reason. So whilst it does the job and does it beautifully, because if I take this, if I take out anyone in the breaker, and I know we're at 1 minute to 5. If you must leave, I understand, right? If we take out any breaker, let us say I take out this breaker, all right? You realize that I am still being supplied. All 4 loads will still be supplied. right? Because I take that out, everything else is connected. So all 4 loads will be supplied just the same. Right? The only problem is I can't apply differential protection to this, which is a major problem. All right. And then lastly, we talk about a breaker and a half. And the term breaker and a half really means that you have 3 breakers used to supply 2 circuits. All right? So if you have 3 breakers supplying 2 circuits, yes, then we technically say you have 2.5 breakers, 1.5 breakers to each circuit. Of course, you can't have a half breaker. Right? So it's 3 breakers to 2 circuits. That's how we need to look at it. And it is very flexible. Note that it is in the mid-range between double breaker, double bus, and single breaker, single bus. All right. So it's in the middle there, between 2 and yeah. So in terms of your figure, this is what it looks like. That's your breaker and a half. So you have 2 circuits. So you have 1 circuit here, you have 1. And then these are the 3 breakers. You have bus A up here, you have bus B down there. Yep. And those 3 breakers would supply the units. So if I needed to supply these 2 while this is out, or if I have a fault on this, if I have a fault on this, then if I have a fault on bus B, these 2 breakers will be out. So they'll separate that bus bar, but the 4 circuits, all right, would still be served by these 4. All right, folks. I know that's a mouthful today. Yeah. But just whilst we absorb all of that mouthful, I still need you to just respond to your names while as we wrap up today.
So, sir, just a question before we move on. So, essentially, the principle behind using breakers in circuits is to use the minimum amount that can provide like maximum functionality of a circuit or grid that you're operating on.
That's the best summary I've heard in a long while. That's exactly what we want to do. We want to provide maximum reliability, maximum efficiency, lowest possible cost. All right? All right, Mr. Adams. Alan?
Here, sir.
Barrett? Spirit? Spirit, not with us. Let me just make sure. Okay. Okay, Blake, Raji?
Here, sir.
Devon,
Here, sir.
Bruce? Buckley? Lewis? Buckley? Burns?
Here, sir.
Campbell?
Here, sir.
Copley?
Here, sir.
Crasdale?
Here, sir.
Daly?
Here, sir.
Jonah,
Here, sir.
Thesis,
Here, sir.
Dwyer, Dwyer. Okay. Ellis,
Here, sir.
Ferguson,
Here, sir.
Finley,
Yes, sir.
Francis,
Here, sir.
Gibson,
Here, sir.
Henry, Henry, Hewitt,
Here, sir.
Jeffrey,
Here, sir.
Johnson. Oh, Mr. Johnson, not here anymore. I need to remove that. Kamika,
Here, sir.
Star,
Here, sir.
Leon,
Here, sir.
Mason,
Here, sir.
Merchant. Is that person in the class? I don't think so. Montague,
Here, sir.
Phillips,
Here, sir.
Porter, Porter, Ramsey,
Here, sir.
Ready, Christoph Reed,
Present, sir.
Dario Reed,
Present, sir. Present.
Rose,
Rose. Rose here, sir.
Russell,
Here, sir.
Shand, Shirley,
Here, sir.
Sinclair,
Here, sir.
Michael,
Here, sir.
Smith, Smith,
Present, sir.
Shanti's here, sir.
Thomas, Thomas, Watson, Williams, Zheng. All right, well, that's it. As I said, I know there's a lot to take in.
Sir.
Yes.
Yeah, before you go, sir, I'm not seeing the images on the school address, sir. And
You sent it a message, you know.
oh, okay, sir. And secondly, sir, I heard you mention the power system protection a couple times in the class, sir. In your experience, is it something that you recommend that other persons inclined to do power engineering to do, or is it a must? I know it's elective, but in your opinion, sir,
You're going to do power engineering.
sir, yes, sir. If you're inclined to do it, sir.
All right. If you're inclined to do power engineering at all, then you really can't go out there to speak with any authority in the area without having some knowledge of protection.
All right, sir.
Because protection looks at not just a transmission system, but it looks at how you protect all, pieces of equipment, power equipment. That is at the core of the power system.
Okay, all right. Thank you, sir.
All right, that's it. Take care. Have a good evening.
You too, sir.
All right,
Have a good evening as well, sir.
Okay, sir. Later.
Take care.